Thank you, Shinji. And thank the organizers for inviting me to this wonderful place. It's my first visit to South Africa, in fact, my first visit to the continent of Africa. And I would like to especially thank Shinji for his patience and not giving up on me. So, I'm going to talk about the subject, Branes and 2D n equals to 2 supersymmetric gauge theories. This is not really a new subject. I mean, the title could have been given 20 years ago, based on work of Ami Hanani and Kentaro Hori. In fact, I will review some of their work in my talk, but then also present several new interesting results. So my next transparency was supposed to be a selection of pictures from the safari that my wife and I went to yesterday and the day before, but unfortunately I couldn't connect to Wi-Fi last night, so I apologize ahead of time, but if you ask me, I'll be more than happy to show you a sample of those pictures. So here's the outline of my talk. I'll begin with a very brief introduction and motivation, discuss some sort of the main aspects of the structure of n equals to 2 theories in 2 dimensions for those that are unfamiliar or for those that forgot, since this was a very popular subject 20 years ago and less so today, although there has been a recent resurgence of activity due to something that I'll mention in the motivation. I'll discuss constructions, embedding n equals to 2, 2 theories in string theory using Brane constructions. First for the case of unitary symmetries, and this is reviewing basically what Ami and Kentaro did 20 years ago now. Then I'll present some new results related to the embedding of theories with orthogonal gauge symmetries. And at the same time, well, if I have time, I would also review symplectic gauge theories, but I'm going to skip that. It's basically the same kind of embeddings, and I decided to be brief and just discuss the embeddings of orthogonal gauge theories. And I'll end with some conclusions. And this is based on work that I've been doing with my graduate student, Oren of Laham, and should appear shortly. So why the interest in 2D n equals to 2 theories? So there's some old motivation and some newer motivation. The old motivation was that these are the theories you want to study as linear sigma models describing 4-dimensional superstring compactifications. Basically, the 4D string compactifications will be described by some n equals to 2 superstring compactifications by some n equals to 2 superconformal theory, and a natural starting point for a 2D n equals to 2 superconformal theory is an n equals to 2 gauge theory, or more generally a linear sigma model with n equals to 2 supersymmetry. More recently, n equals to 2 theories have arisen in the description of world sheet theories describing the self-dual strings that are the basic object in the 6D 2, 0 and 1, 0 superconformal field theories, which are of course very interesting these days. More generally, there's been a lot of work on 4D theories, 3D theories, 5D and 6D theories, and in parallel there has been some recent work on relating properties, particularly dualities, across dimensions, how 4D dualities reduce to 3D dualities upon reduction, circular reduction, and similarly one can ask about how 3D dualities relate to 2D dualities, and these are the kind of theories where those dualities naturally arise, as we will see. And finally, we have new computational tools, all stemming from the idea of supersymmetric localization. And for 2D theories, this is useful for computing what's known as the elliptic genus. So we know now how to compute these objects exactly given the gauge theory Lagrangian. And so it makes sense to go back and look at these theories and various conjectures that were given for these theories in terms of dualities and counting supersymmetric ground states, and test these conjectures using these new computational tools. And specifically, formulas for the elliptic genus for various gauge theories with n equals to 2 theories were only written down in 2013 by Benini, Hori, and Cremonesi, I think. Or maybe it's Tachikawa, sorry, it's Tachikawa. Okay, so what can Branes teach us about 2D n equals to 2 theories? Basically the same kinds of things that, it's the same slogan that we have, we've always given, namely that embedding in string theory in terms of Brane constructions provides a geometrical description of all the properties in the field theory, some of which we know and some of which we don't know, strong coupling properties of the gauge theories, in particular dualities. And it works both ways. Sometimes the geometrical description teaches us something new that we hadn't realized previously about the field theory, and sometimes something that we know about the field theory from other calculations teaches us something new about Brane dynamics and string theory. Okay, so we'll see examples of both things today. And also, well, 4D and 3D theories have been studied extensively, have been embedded extensively in string theory and in M theory. 2D theories not so much. Well, there's the work of Ami and Quintero from 1997, but since then, pretty much, there hasn't been any developments in looking at n equals to 2 gauge theory from this geometric point of view, embedding them in string theory. Okay, so a little bit about the basic structure of n equals to 2 theories. This may be very familiar to many of you, but maybe not, a bit less familiar to the younger people. And basically the relevant reference is Ed Witten's paper by Ed Witten from 1993. N equals to 2 theories have two sets of supercharges called Q plus, with Q plus tilde, and Q minus and Q minus tilde. These carry charges under one. There are two U1 or two SO2 R symmetries, or U1 R symmetry that we call U1 R and U1 left because it's 2, 2. One set of supercharges is charged under U1 R, the other set under U1 L. And this is the dimensional reduction of n equals to 1 in 4 dimensions. So there are chiral multiplets, the usual chiral multiplets, the complex scalar field, and 2 fermatic degrees of freedom. In 2 dimensions, we split them into psi plus and psi minus. And there's the usual vector multiplet, well, the dimensional reduction of the vector multiplet, which has 2 components of the gauge field. It has a complex scalar field sigma, the gauginos, and the auxiliary scalar field D. What is sort of new in the 2-dimensional equals to 2 theories is that the field strength of the vector multiplet can be repackaged as what's called the twisted chiral multiplet, which looks a lot like a chiral multiplet, except instead of theta minus, it comes with a theta minus bar. So there's theta plus as usual, but instead of theta minus, you have a theta minus bar. Okay, and that's because you have these 2 possibilities of Q plus and Q minus. Okay, so that's the basic ingredients. Everything which is not, and well, this transparency will give basic description of everything which is not the usual reduction of n equals to 1 in 4 dimensions. Superpotential, Kähler potential, all the things that we know and love about n equals to 1 in 4 dimensions. But there are some new novel structures that arise when you have 2D theories with 4 supersymmetry, just 2, 2 supersymmetry. Basically 3 types of novel structures. First of all, there's a complex Coulomb branch, okay, because we're in 2 dimensions. So the two components from 4 dimensions along the reduced directions become a complex scalar field. So there's a Coulomb branch, a complex Coulomb branch, labeled by the complex field sigma in the vector multiplet. In addition to being able to turn on the usual complex mass parameter as a superpotential term, there is a novel structure called the twisted mass deformation. Get rid of that person. Yeah. Which arises in this way. One can think of this as coupling a chiral multiplet phi to a vev of a background, of a scalar belonging to a background vector multiplet. Okay, and that's And that, so you can do that with a single chiral multiple. Of course, the complex mass requires phi and phi tilde. And there's something called a twisted superpotential. In addition to being an ordinary superpotential, one can have a twisted superpotential, which is a holomorphic function of twisted chiral superfields. And in particular, the gauge field, the field strength of the vector multiplet is such a field. So one can have such an object integrated over theta plus theta minus bar, because it's a twisted superpotential. And the simplest kind of twisted superpotential, which is what arises in general as a classical superpotential for a unitary gauge theory, is a complexified version of the Fi term, of the Fa-Eleopolis term, T trace sigma, where T, the real part of T is the Fi term, and the imaginary part is the Yang-Mills theta parameter.
I ask a question?
Yeah.
So if I were n equals 2 3D theories, and I say dimensionally reduced to 2D, does the real mass in 3D, does that become the
yeah,
twisted
the real
mass?
mass becomes the twisted mass.
Okay.
That's right. So the twisted mass is complex. M tilde is a complex parameter.
Yeah, okay.
One part of it comes from the real mass deformation of 3D. So it's something that, okay. So in some sense, it's not that novel. I mean, it's something which you have in 3D.
Right.
It's certainly novel compared to 4D. But what's novel in 3D is it's a complex parameter.
Okay. Right.
I mean, also in 3D, you have a real scalar, a real range in some sense. Okay, but the twisted superpotential is genuinely a new structure. Okay, so that's classical. There are interesting quantum effects. In particular, generically, the Fi and theta parameters are renormalized in one loop. So we can start with the classical piece, T trace sigma, but generically they'll be renormalized at one loop when you go out on the Coulomb branch of the theory. And the generic structure, and it's one loop exact, the generic structure has this linear times logarithmic corrections, where R is the rank of the gauge group and W is just a collection of all the weights that the theory has. So this gets contributions from W bosons and also from any matter fields that exist in the theory. And what this means is that the Coulomb branch may actually be completely lifted in these theories. You generate the potential for the vector multiplet, in particular the scalar of the vector multiplet. So generically the Coulomb branch will be completely lifted. And that's a good thing from the old viewpoint of string compactification, where we want to have a discrete spectrum for the 4D theory. And it's also good for us, from our point of view, since our point of view is we want to sort of discuss interesting IR dynamics and IR dualities, and there we really want to sort of get rid of this Coulomb branch. Coulomb branch sort of is not a good thing to have if we want to really discuss the IR properties of what the ground state of the theory does. So we want to get rid of these infinite, large, infinite-sized Coulomb modules called Coulomb branches. Okay, so let me review a little bit results related to unitary gauge theories. And this is based on a paper of Hanami-Morris from '97. So on the effective twisted superpotential on the Coulomb branch looks like this. So T is the classical piece. Remember, T is just the classical Fi term, complexified Fi term, which Fi term plus I times the theta parameter. Then there's a contribution from the W bosons. K is the rank of the group. That's just a linear term, so and it's imaginary. There's an I here. So the W bosons simply shift the theta parameter by a multiple of pi. Okay? So since the theta parameter has a periodicity of 2 pi, it's either 0 or not or pi, depending on whether K is even or odd. And this is the contribution of matter fields. So in particular, Ami and Vitaro considered NF fundamental, NF chiral multiplets in the fundamental representation, and that contributes this term. Then one can sort of derive the various properties of these theories by studying the moduli space, Coulomb branch, a moduli space, and In particular, one can show that supersymmetry is unbroken as long as the number of flavors is greater than k, and if that holds, then there are multiple, the number of supersymmetric ground states is given by nf choose k. The lower bound, nf equals to k plus 1, is a theory that flows in the infrared to a free theory of the baryons. And for nf greater than k plus 1, the theory exhibits Seiberg-like duality relating the UK theory to the UNF minus k theory. Right? So you can show that the moduli spaces are the same and the anomalies match, just like Seiberg duality in 4 dimensions. Note, in this case, there are no additional fields in the magnetic theory, okay? Because this is just NF fundamentals. So this is not what you would call NF flavors, which include both the same number of fundamentals and anti-fundamentals. Okay? So in 2 dimensions, you can actually just have fundamentals without anti-fundamentals. But you can also have anti-fundamentals as well as fundamentals. And this was studied some years later by Kintaro and Hori and David Tong. And in particular, the result, if you have an equal number of fundamentals and anti-fundamentals, then the logs cancel, but there's sort of a linear residue, and you just get a linear effective twisted superpotential, which is shifted by I pi times n plus k minus 1. N is the number of flavors, k is the rank of the gauge of UK. And so the only effect the only effect that one has in one loop is to shift the theta parameter by this integer multiple of pi. So if this integer is even, then it's nothing, and if it's odd, then it's a shift of pi. Okay, so we're interested in embedding 2D gauge theories in string theory, and the way to do that, just like the embedding of 4D theories, is to go to type 2A string theory and build a brane construction using D branes suspended between a pair of NS5 branes, and those are traditionally called the NS5 brane and the NS5 prime brane. The geometry is shown here. The D2 brane fills the directions 1 and 6. I've drawn here the 6-7 plane. And for the generic case where we have NF fundamentals and NF anti-fundamentals, then we will have that we'll get by putting NF semi-infinite D4 branes extended in one direction in the 7 coordinate, ending on the NS5 brane, and NA semi-infinite D4 branes extended in the other direction in the 7 coordinates. Okay, so this describes NF fundamentals and NA anti-fundamentals under the UK gauge symmetry of the effective 2-dimensional supersymmetric gauge theory living on the 2 branes. And as usual, the inverse gauge coupling is related to the separation of the NS5 branes. If the number of fundamentals and anti-fundamentals is equal, n, then all the 4 branes, the upper 4 branes can connect with the lower 4 branes, and we can move them as the whole infinite 4 brane into the interval, getting a configuration. I think this is sort of the naive configuration that anyone would draw these days to describe a gauge theory with some number of fundamental fields, some fundamental chiral multiples. Okay, but there's a more general picture in the 2D theory, okay, and this is unique to 2D, where you can have a different number of fundamentals and anti-fundamentals. Okay. So we're going to be generalizing this story to orthogonal gauge theories, where you actually have there aren't fundamentals and anti-fundamentals, there are just fundamentals, and that corresponds to, if you were to lift the theory to a unitary theory, or project down from unitary to orthogonal, that would require an equal number of fundamentals and anti-fundamentals. So in our configurations, we will always mostly be able to put the 4 branes inside the interval, with one exception, which I will discuss. As usual, the parameters and moduli of the field theory are described in a geometric way using positions of the branes. In particular, the complex mass parameter corresponds to pulling the 4 brane away from the 2 brane in the 4, well, this should be 4 or 5 direction because this is a complex parameter, but so 4 should be 4 or 5. And the twisted mass parameter corresponds to pulling the forebrain out in the 2 or 3 direction. And if you just pull the forebrain, the infinitely forebrain up in the 2 or 3 direction, that corresponds, so now we have both fundamentals and anti-fundamentals, but a twisted mass parameter can be turned on separately for the fundamentals and anti-fundamentals. Pulling the forebrain as a whole corresponds to the case where those two twisted mass parameters are equal, I denote them m tilde and m hat. But more generally, they don't have to be equal, and that corresponds to, and well, in the brane configuration, that can be seen by putting the forebrain at the edge of the interval, where it coincides with the NS5 brain, and then breaking it into 2 semi-infinite pieces. Okay? And the position of one semi-infinite piece is the twisted mass of the fundamental, and the position of the other the opposite semi-infinite piece is the twisted mass parameter of the anti-fundamentals. So remember, this is the 2 and 3 directions, and the position of the 2 brane in the 2 and 3 directions as it slides up and down those directions which are shared by the 2 and 5 brane corresponds to the Coulomb, the complex Coulomb modulus sigma. Okay, we can also describe the Higgs branch in this picture. That corresponds to breaking the 2 branes between the flavor forebrains. And sort of here I describe the picture showing the maximally Higgs situation, where I've broken as much as I can. And what I mean by that is that there's a rule that one must obey in how one breaks these, and this goes by the name of S rule. The S rule is a rule that tells us how many 2 branes we can stretch between an NS5 brane and a D4 brane, at most 1. And so the breaking has to respect that rule. So you see this 2 brane connects here, this 2 brane connects here, and this 2 brane can connect here. But you can't have two branes connecting to the same 4 brane, and so that limits the possibilities of breaking. And that's how one realizes the Higgs branch. And this also shows, so here we're on the Higgs branch, and we can count how many possibilities we have, because I have the S rule, but then I have some combinatorical possibilities of which 2 branes end on which 4 brane, and that combinatorical problem just gives us n choose k, okay? Exactly as the field theory told us, so they're n choose k supersymmetric ground states. Okay? So I have to obey the S rule, otherwise I break supersymmetry. Any questions? Okay, there were a couple of other parameters in the field theory. There's the Fi parameter and the theta parameter. The Fi parameter is realized as the separation of the NS5. By the way, I'm going to be flipping between, instead of drawing confusing 3D, I'm always confused by these attempts to draw 3D brane configurations. So I'm only going to draw them 2D, and I'm going to be going like back and forth between different sets of coordinates. The horizontal direction is always going to be the 6th direction. That's the direction of the interval. And then when I'm going to switch between different y-axes in describing different parameters and moduli. So the Fi parameter corresponds to the separation of the 2 NS5 brane in the 7 direction. And you can see that when you separate them in the 7 direction, that forces the 2 branes to break. So they're reproducing the feature that the Fi term forces you onto the Higgs branch. The theta parameter is something that is not immediately visible in the type 2A brane configuration, and you have to go to M theory. In the lift to M theory, of course, the 2 NS5 branes become 2 M5 branes, which we call M5 and M5 prime. The D2 branes become M2 branes, and the D4 branes become also M5 branes. But these are parameters that are wrapping the extra direction of M theory, which is 10. And the theta parameter is then nothing but the separation of the M5 branes, of the M5 and M5 prime brane in the 10 direction. So it's basically the same kind of object to the Fi parameter, and they form this complex parameter from the point of view of the gauge theory. More generally, okay, so here I've been concentrating on the specializing to the case where the number of fundamentals and number of anti-fundamentals is equal, so you just have n flavors. More generally, if they're not equal, then as we saw, we can't pull off all of the forebranes. We have a mismatch of semi-infinite forebranes going in opposite directions in the 7th direction, and so we can't connect all of them. We can connect some of them, but then some will remain. And that will live to a configuration where some M5 tilde branes are not in the interval, but are sort of ending on the M5 prime brane, and that sort of forms this complicated configuration of a single M5 brane on some complicated curve. And then, as Ani and Gintara showed, this curve precisely reproduces the logarithmic renormalization of the Fi and theta parameters. However, this will not play a role in the rest of my discussion. So, because as I said, we're going to consider only the case for an equal number of fundamentals and anti-fundamentals. Any questions about unitary theories? Or anything else? Okay. Oh, I'm still unitary theories. Why? Ah, yes. Of course. Cyber duality. So, well, cyber duality, from the point of view of the brane construction, is basically the same game as it was in 4 dimensions and in 3 dimensions. We do 2 things. The first thing we do is we pull the forebranes out of the interval to the right, across the NS5 brane. Then, as everyone knows, each such crossing creates a D2 brane, and now the flavors, instead of being described by the forebranes, they're described by these outside D2 branes. The strings connecting the outside D2 branes and the inside D2 branes are the matter fields. This is the UK plus N theory. And to get the dual theory, we exchange the NS and NS prime, the NS5 and NS5 prime branes as follows. First, we separate them in the X7 direction by turning on an F5 parameter. So now this one is connected by KD2 branes and this one by N minus KD2 branes. Then we move them across each other without ever touching in the X6 direction. And this is important because if they touch, then we have to deal with strong coupling dynamics of intersecting 5 branes. And then we close the F5 parameter again. And we land on the theory UN minus K with N flavors plus N squared singlets. I think I skipped that somehow when in the transparency when I was discussing the field theory, the duality from the point of view of field theory. But anyway, so this is the one that's similar to the 4D cyber duality. U K plus N is dual to UN minus K plus N with N squared, with a meson, with N squared singlet mesons corresponding to the degrees of freedom of the outside D2 branes to slide in the 2 directions that are shared by the NS5 prime brane and the D4 brane. So here they didn't exist because these 2 branes don't share any directions. Here they share 2 directions, and those degrees of freedom correspond to the N squared singlets. Okay, so this is very similar to the cyber duality. Okay, so now, are there any questions about unitary theories? Okay, so now we'll move on to the new part of my talk, the construction of orthogonal gauge theories in 2 dimensions. I'll begin by summarizing the field theory results. So we consider orthogonal 2D n equals to 2 orthogonal gauge theory with n fundamentals, n chiral superfields transforming into vector representation of OK. And this is based on work that Gintara did in 2011. In that case, the effective twisted superpotential is linear, again because this is basically the same structure as the UK theory with with an equal number of fundamentals and anti-fundamentals. So there are no logs, there's just a linear correction. There's no tree-level Fi term. There's no Fi term for the orthogonal gauge theories, but there is something that you can turn on classically in an orthogonal gauge theory that I've denoted here as theta sub d, known as a discrete theta parameter. So it's an analog of the theta parameter of the unitary theory, except it's not continuous. It can take only 2 possible values, which in our normalization are 0 and pi, and it's associated with the fact that the fundamental group of of O or SO is Z2. So there is a related instantonic configuration in 2 dimensions which carries a Z2 charge. And the theta parameter sort of is the weight factor that goes into the path integral in that instanton sector. Okay, so I'll just summarize the results that Kentaro found and or conjectured in 2011. So first of all, this is computed exactly to one loop, and then it shows that the Coulomb branch is lifted or not lifted, depending on the relative parity of n plus k and theta. So if n plus k is even, n is the number of fundamentals, k is the group integer. If n plus k is even and theta is equal to pi, then you see you have an odd multiple of pi. Or if n plus k is odd and theta d is 0, then again you have an odd multiple of pi. There's a linear potential, a linear twisted superpotential generated. The Coulomb branch is lifted. Supersymmetry is unbroken under the condition that n is greater than k minus 2. The counting of the number of supersymmetric ground states depends on whether n and k are even or odd. So there are again formulas like n choose k or n over 2 choose k over 2, things like that. And it depends. The details depend on whether n and k are even or odd. For n, if n is equal to k minus 1, the boundary, the borderline case, the theory, again, as the theory, just like in the UK theory, flows to a free theory in infrared, in this case the theory of the mesons. For n greater than k minus 1, there is a Seiberg duality, again, so you have 2 theories that flow to the same interacting fixed point in the IR. And in this case, the duality relates OK to On minus k plus 1, together with a symmetric meson. So this is n times n plus 1 over 2 mesons with the usual superpotential coupling between the mesons and the dual quarks, the magnetic quarks. Okay? So the one interesting thing to note here is the shift of 1, okay, which didn't exist in the unitary case. And this is reminiscent of an analogous shift in 4 dimensions of 4. Okay? So in 4 dimensions, the duality for the orthogonal gauge theories contains, it would be OK is dual to ON minus k plus 4. In 3 dimensions, you can guess it's 2. Indeed it is. And in 2 dimensions, it turns out to be 1. So there appears to be sort of a structure here related to the number of dimensions. So one of the things that we will need to do in the brane embedding is to sort of reproduce this, in particular reproduce this plus 1. Okay? That will involve some non-trivial brane dynamics. Okay, so here's the brane construction. The brane construction of an orthogonal theory will obviously involve an orientifold plane. So we add an orientifold 2 plane parallel to the D2 branes. That orientifold, well, to get an orthogonal gauge symmetry, there's 2 possibilities. It's either what's called an O2 minus, which is the usual orientifold plane, or an O2 minus tilde, which is a variance, the one that gives you the one that differentiates between O2k and O2k plus 1. Together with KD2 branes, and I'm going to try and keep to a convention where what I mean by KD2 branes are KD2 branes and their images. Okay? So this will describe either an O2k theory if it's O2 minus, or an O2k plus 1 theory if it's an O2 minus tilde. Okay? And I have 2n, an even number of D4 branes in this case. So this will describe a theory with an even number of flavors, an even number of matter fields in a vector multiplet. But of course, nothing prevents us, from the field theory point of view, having an odd number of flavors. And to do that, we actually we need an odd number of D4 branes. And so, well, properly taking into account the action of the orientifold on the 4 branes forces them to be paired up. And the only way to add an unpaired D4 brane is if it's not really a complete D4 brane, but it's 2 halves of opposite semi-infinite D4 branes. Okay, so this D4 brane is sort of stuck here because it's built of 2 semi-infinite D4 branes, each of which is ending on the NS5 prime brane from the 2 directions. And I forgot to draw the axis here. Of course, the horizontal axis is the 6th direction. In this picture, the vertical axis is the 7th direction. It's the direction in which both the NS5 and the NS5 prime are localized. Okay, so this is the construction for an even number of flavors. This is the construction for an odd number of flavors. In particular, I can move, for the odd number of flavors, I can move 2n of them into the interval, but 1 is forced to stay there. In addition, the NS5 branes themselves are stuck on the orientable plane. They are their own image. They cannot move away from the orientable 2 plane. And as I said, the O even theory corresponds to having an O2 minus, and the O odd corresponding to O2 minus tilde. And if I want to discuss symplectic gauge theories, then I would replace O2 minus by O2 plus or O2 plus tilde. In addition, there is one further complication to the story, and that is that the NS5 branes actually change the type of orientable plane. Right? And also the D4 branes change the type of orientable plane. So when I go across an NS5 brane, which is stuck on the orientable plane, it actually changes it from O2 minus to O2 plus or vice versa, and from O2 minus tilde to O2 plus tilde or vice versa. And when it crosses a D4 brane, it places a tilde or removes the tilde. Okay, so that's another reason to sort of understand the requirement of having an even number of D4 branes in the interval, because if there was an odd number of 4 branes in the interval, then you wouldn't, it would be difficult to identify, what is this theory? Is it an orientifold 2 minus or an orientifold 2 minus tilde? Well, on one side of the 4 brane it's this, on the other side of the 4 brane is that. Okay? So in this construction, you never come across that confusion. I'm always, these 4 branes are always together, and so this orientifold plane is of one type. But because of this this effect where the branes, the NS5 and the D4 branes, change their orientifold type, the type of orientifold plane on the outside is going to be different. Okay? The theory is determined by the type of orientifold plane in the interval, because that's where the D2 branes are. But because of this, the type of orientifold plane on the outside will be different because you're going across an NS5 brane. So if it's an O2 minus on this side, it's an O2 plus on this side. And similarly, in the other construction, here you're going across both an NS5 brane and a single D4 brane. So if it's an O2 minus on this side, it's going to be an O2 plus tilde on this side, and the other possibility. Is that point clear? Okay, so we can realize geometrically the various parameters of the theory. We have complex mass deformation. In this case, we have to pull the 4 branes off in the 4 or 5 directions pairwise. So if we have, so the brane construction seems to only allow us to turn on complex masses pairwise in opposite sign pairs. I think from the point of view of the field theory, there isn't any issue with just turning on one complex parameter, as far as I know. It's one of those cases where the brane construction doesn't quite realize all the possible deformations of the field theory. So it seems to, for the complex mass deformation, it seems to require turning them in opposite sign pairs. The twisted mass deformation corresponds to, in this case, we can't pull the 4 brane as a whole into the 2 direction or 3 direction. The orthogonal symmetry requires us, the projection requires us to turning on the twisted masses in opposite sign pairs, just like the complex masses. And we can do that by breaking the 4 brane into its 2 semi-infinite parts along this 2-3 plane, equal distance in opposite directions. So n tilde is minus m. There's no Fi parameter, as we said, for orthogonal gauge theories, and there's no continuous theta parameter, but there's a discrete theta parameter. The orthogonal gauge theory in 2 dimensions admits a discrete theta parameter. And just like in the unitary theories, to see that discrete theta parameter geometrically, we need to go to M theory. We need to lift this construction to M theory, to an M brane construction. Okay, so let's do that. So we need to discuss, so we know how to lift the original configuration without the orientable plane. So the only thing that's missing is now to discuss how the orientable plane itself is lifted to M theory. And this was shown by Ami and Balakot in 2000, the orientable two-plane lifts to a pair of objects called ON2 planes, which are orbifolds, the orbifold in M-theory C4-1Z2. This object has two variants called ON2 plus and ON2 minus. And the O2 plane lifts to two of these guys on sort of opposite sides of the X10 circle. And there are four possibilities, because there are two choices of which O2 plane goes here, which O2 plane goes here. So and correspondingly, there are four orientable planes, and the translation table is shown here. For example, the O2 minus corresponds to O2 minus, two O2 minuses. The O2 minus tilde corresponds to two O2 pluses, and the others are shown here. And in particular, from these relations, we can compute the charges, given the charges of the two O2 planes, which are 3/16 and -1/16. By combining them in these four ways, we get the correct charges for the orientable planes. So the O2 plus or minus planes have a charge plus or minus 1/8, and the O2 minus tilde plane has a charge 3/8, and the O2 plus tilde plane has a charge 1/8. And similarly to the situation in type 2A string theory, where the NS5 branes and the D4 branes cause a change in the type of orientable plane, the analogous thing also happens in M theory. Each M5 brane, which is fractional in the sense that it's stuck on the ON2 plane, changes the type of ON2 plane between ON2 plus and ON2 minus. Okay. So what is the discrete theta parameter? So the continuous theta parameter corresponding to the relative position of the two M5 branes in the 10 direction. Now the M5 branes cannot move in the 10 directions because they're stuck on an ON2 plane, which are localized in the 10 direction, but there are two ON2 planes. So there are two distinct possibilities. Right, and the discrete theta parameter will correspond to those two possibilities corresponding to the discrete relative X10 position of the M5 branes. So one possibility is that the two M5 branes, the M5 and M5 prime, are on the same ON2 plane. So something like this for the case with an even number of flavors. So this is the 10 direction, this is the ON2 plane, say at 0, and this is the ON2 plane at 2 pi. I've denoted the signs here are shorthand for ON2, so the upper sign corresponds to the ON2 minus, the lower sign corresponds to the ON2 plus. So see, since you're going across an even number of M5 branes, the overall sign doesn't change. Here I start with a plus minus, going across the M5 prime brane, it becomes a minus plus, and then going across the M5 brane, it flips again, the plus minus. Okay? The reason I've chosen here minus plus and here plus minus is because I want to discuss the orthogonal gauge theories. And you can see that this gives the orthogonal gauge theories because now, if you look at the sign in the interval, it's minus plus up here, and it's minus plus down here, which means it's either minus up and minus down, or plus up, plus down. So if you remember the translation table from the previous transparency, minus minus is the O2 minus, which is the theory which gives the gauge theory O2k, and plus plus is the O2 minus tilde, which gave the odd orthogonal gauge symmetry O2k plus 1. Okay? And these will have some discrete theta parameter, and so it's either 0 pi. It turns out the correct identification is that for the case of O2k, namely the upper sign choice here and here, this is a vanishing discrete theta parameter, and for the other case, the O2k plus 1, this is the theta parameter pi. And this is for an even number of flavors, right? We have 2n D4 branes, and those lifted to 2n, what I call M5 tilde branes. Those are the lifts of the D4 brane. And if I want to construct lift the brane configuration for the odd number of flavors, I have this lone D4 brane, which was built of two semi-infinite pieces in the 7th direction. So those lift to an M5 tilde brane, which is ending on the, which again is sort of gluing two semi-infinite M5 tilde branes in the X7 direction, both ending on the M5 prime brane. So in this case, we get an odd number of flavors, 2n plus 1, and again, depending on the relative sign, it's either the O2k gauge symmetry or O2k plus 1, and the theta parameters turn out to be different than the ones here. Different but definite. Okay, so what can we learn from this picture? One thing we can learn from this picture immediately is that there is a Coulomb branch, which is not lifted. The Coulomb branch remains, and these are what Kantaro called irregular theories. The theories that will not have nice normalizable low energy dynamics and dualities because they have a Coulomb branch. Well, the Coulomb branch is described by the motion of the M2 brane in the two directions that are shared by the M5 and M5 prime. The other possibility is that the two M5 branes can be on different OM2 planes. So one can be on the upper and the other can be on the lower, or vice versa. Of course, those are identical. We just rotate the circle by pi. Okay? So here we have so I've raised the M5 prime brane to be on the upper OM2 plane. That forces the M2 branes initially sort of be oriented in this diagonal way. This is the case for an even number of flavors. This is the configuration for an odd number of flavors. And you'll notice that the theta parameters are the opposite of what they were on the previous page, right? So I've changed the relative position of the M5 branes, and I claim that just like the relative position of the two M5 branes without the OM2 plane was the continuous theta parameter for the unitary theories, the discrete relative position, namely whether they're on the same OM2 planes or different OM2 planes, is in one-to-one correspondence with the discrete theta parameter of the orthogonal theory.
What about susy?
Yes, so this configuration breaks supersymmetry, and I will show you, and we will see what happens. There is a configuration which is supersymmetric, again, under some condition, under some requirement relating the number of flavors to the rank of the gauge. So the first thing we notice here, as I said, the Coulomb branch is lifted. Okay, so this configuration breaks supersymmetry. I should have left this statement for the next transparency anyway. Breaks supersymmetry, and in particular, well, it breaks supersymmetry because the M2 branes are at an angle compared to the OM2 planes. That angle is not 0 degrees. And what goes along with that breaking is that the Coulomb branch is lifted. So these are what Kantaro called the regular theories. Okay, but actually we will see more clearly the lifting of the Coulomb branch in the next transparency. Okay, so lifting the Coulomb branch and counting supersymmetric ground states. So what happens clearly is that there is another configuration. So the M2 branes were diagonally, but of course there's another configuration carrying the same charges, which naively is supersymmetric, where the M2 branes are forced to break. Okay, so this piece of the M2 brane is parallel to the M2 plane, and this piece is also parallel to the M2 plane, but they're forced to break. And I've shown here sort of a generic point on the Higgs branch of the theory. So here clearly you can see why the Coulomb branch is lifted. Well, you're basically forced onto the Higgs branch. You can no longer move the M2 brane along the M5 branes because the M2 brane is broken. Okay? It's no longer connecting the M5 and M5 prime. Applying the S rule again, in this case, for the case of an even number of flavors, shows. So I use big N for the number of flavors, and for the even case, it's set equal to 2 little n. And remember, this is the theory which is either O2k or O2k plus 1 with lowercase k. And supersymmetry here, the S rule requires n to be at least as large as k. Otherwise, you will have at least two M2 branes ending on at least one M5 tilde brane. And then a simple combinatoric counting shows that there are M2's k ground states. The case with an odd number of flavors is a little trickier because there's an additional flavor brane which is not inside the interval. It's sort of ending on the M5 prime brane. So we have to be a little bit more. We have to do a little more work there. In particular, we're going to need sort of an extended version of the S rule to do the counting of the supersymmetric ground states, or even to discuss, the condition for unbroken supersymmetry in that case. Okay, and so this will be an aside on that story of extending the S rule for the case of fractional M5 branes, M5 branes that are stuck on the OM2 plane, and that will be related also to an extension of the brane creation effect for that case. Okay. So the basic configuration is this. We have an OM2 plane and we have an M5 brane, we have an M5 tilde brane. Okay? And these two branes don't share any directions. They're what are called linked. They're a linked pair, and one can define a linking number. For example, from the point of view of the M5 brane, that linking number gets two kinds of contributions. One, it's basically counting the number of the linked 5 brane on the right minus how many linked 5 branes you have on the left. Except because that other 5 brane is also fractional, there's well, okay, so that comes with a 1/2, and my counting here is that this number will also be 1/2 because this brane is fractional. And the other contribution counts the number of the M2 brane charge, sort of terminating on the left side of the M5 brane minus the M2 brane charge terminating on the right side of the M5 brane. So it's basically the same definition of the linking number that is used in flat space. We're going to use in the background of the OM2 plane. So it's the same formula as in flat space, except that here these numbers will actually be fractional. They'll be quantized in units of a half because of the presence of the OM2 plane. Okay, so brane creation occurs in order to preserve linking numbers. So we exchange the M5 and the M5 tilde brane, and what happens to the linking number? Okay, so the linking number of the original configuration is this. We get a -1/4 because from the point of view of the M5 brane, we have one M5 tilde on the left, right? So we get a minus. That's a fractional M5 tilde, so this contributes to 1/2. 1/2 times 1/2 with a minus sign, so that's the -1/4. And then we also have a contribution from here because the charge of the OM2 minus, well, so A here is either plus or minus 1, right? So because the M5 brane changes the charge of the OM2 plane, there will be a difference between the M2 brane charge on the left and on the right. And for this configuration, it's minus A over 4, where this is here, this is OM2 minus A, this is OM2 plus A. Right? So this is the linking number of this configuration, and then the change in the linking number, the would-be change in the linking number, is gotten by subtracting that from the linking number for the M5 brane computed in this configuration. So here we have a positive 1/4 because the M5 tilde is now on the right, and we have a positive A over 4 because also the charge difference, the M2 brane charge difference across the M5 brane also changed sign. The net result is a would-be change in the linking number of minus the quantity 1 plus A over 2, where A is either plus or minus 1, right? Because I either start on the left side with an OM2 plus or an OM2 minus. Okay? So it's 0 if A is equal to minus 1, and it's minus 1 if A is equal to plus 1. And so, a single M2 brane must be created if A is plus 1, and no M2 brane should be created if A is minus 1 in order to preserve the linking number. You see, if A is equal to minus 1, there's no change in the linking number, so we don't need to create an M2. So I denoted that here by 1 plus A over 2 M2 branes. So that's basically either 0 or 1. Okay, that's sort of interesting. Brane creation effects in flat space, are sort of fixed. Once you exchange the M5 brane, branes are created. But here, or annihilated, depending on the orientation. But here, it's a choice between creating a brane or not creating a brane. And so, and related to this is a sort of its contribution to the S rule, and that is the case where one brane is created means that we could have started with one brane, with either no brane or one brane to begin with, and then once we exchange, if we had one brane initially, the exchange would reverse its orientation, making it an anti-M2 brane, but because we created an M2 brane, those can annihilate, and we would still preserve supersymmetry. But had we started with two M2 branes, we would have two anti-M2 branes, plus one M2 brane equals one anti-M2 brane breaking supersymmetry. So that's just a quick review of how the S rule is sort of derived from the brane creation effect. So the conclusion is that for a configuration like this with A is equal to plus 1, we can have either 0 or 1, but at most 1 M2 branes connecting them. and we cannot have any M2 branes connecting them if A is equal to -1. Okay, so armed with this extension of the S rule, we can now come back to the case with an odd number of flavors. How much time do I have? 0?
No, 10 minutes.
10 minutes, okay. So armed with that, we can come back to the case with an odd number of flavors. Here it is. This is the picture of the Higgs branch. And we want to sort of count ground states, or to begin with, we want to sort of determine the condition under which this configuration is supersymmetric. And we have to take into account the new S rule, which is this blue M2 brane. So you can either have this blue M2 brane or not have this blue M2 brane, depending on the two cases that I discussed previously. And well, I mean, if you look at, you can figure out which case is which according to these signs. And the bottom line and the upshot is that supersymmetry requires n to be greater than k minus 1 for O2k, and n to be greater than or equal to k minus 1 for O2k, and n to be greater than or equal to k for O2k plus 1. Okay? So if you go back to the original notation with capital K and capital N, this and also the previous result for the even number flavors is in perfect agreement with the quantum field theory result, a condition that capital N is bigger than capital K minus 2. Okay, so that brings us to cyber duality. So remember, in the unitary gauge theories, the brane description of cyber duality was exchanging the two NS5 branes. And it was important that we had the Fi parameter, the relative position in the x7 direction, that allowed us to make this exchange without the NS5 branes ever meeting in space, so without ever having to deal with strong coupling dynamics. We can't do that here because we can't move the NS5 branes in the 7 directions. There's no Fi parameter for the orthogonal gauge theories. So if we exchange the two NS5 branes, they won't necessarily meet in space. Okay? They won't necessarily cross. So in principle, one has to deal with strong coupling dynamics in this case. Now, something similar happened in and part of strong coupling dynamics may or may not be the creation of additional D2 branes from the crossing of the NS and NS5, even though naively these are not a linked pair, like the NS5 and the D4. Indeed, this is exactly what happens in 4 dimensions, as shown by Evans, Johnson, and Shapir, also 20 years ago, in discussing brane constructions of orthogonal and symplectic gauge theories in 4 dimensions and sort of realizing geometrically cyber duality in that case. So if you start with this configuration that describes orthogonal n equals to 1 theory in 4 dimensions and perform the duality move, the cyber duality move, and changing the two NS5 branes, they showed that there is the creation of 4 D4 branes. Okay? Even though there are no flavor branes involved here, there are no D6 branes, still four branes, which means 2 and 2 images, are created just from the exchange of the NS and NS prime. And there is a linking number argument that shows this. One can also argue it from the point by lifting the M theory. However, if you try and apply this argument in the 2D case, in the type 2A brane construction of our 2D orthogonal gauge theory, it seems to fail, and it seems to fail because the counting. I should also mention that the same kind of argument for 3-dimensional theories gives the creation of 2 D3 branes, and that's why there's a shift of 2 in the orthogonal duality in 3 dimensions. Sort of trying to push this argument to 2 dimensions would suggest that you'll create a single D2 brane, okay, which is a fractional D2 brane which is stuck on the O2 plane, which is kind of strange because naively you would think that changing an O2 minus to an O2 minus tilde, which is the one with the one fractional D2 brane, requires a D4 brane to have been around somewhere. And in this argument, applied to 2 dimensions, we don't have any D4 branes anywhere. We just have 2 NS5 branes that are crossing. So we don't expect a creation of a single D2 brane. Okay? Of course, that would explain the shift by 1 in the cyber duality. Okay? But this argument, applied naively, seems to fail. We will actually see how to fix this argument, and that will be the last thing I'm going to say from the type 2A point of view. But first, let me show you how this is resolved in a very simple way in M theory. Okay? The issue is resolved in M theory Because in the regular theories, the lifts of the two NS5 branes don't actually cross in space because they are sitting on different O and 2 planes. Okay? So for example, for the case with an even number of flavors, so I'm going back to the configuration before the M2 branes break and pulling the flavor branes out on the right, again to sort of build the duality, how the duality is realized in the brane configuration. So this is the theory with an even number of flavors. And then you see there's no problem in exchanging the two M5 branes. They never touch in space. We just move this one to the left and this one to the right and this one to the left. Okay? And then initially we have K on two branes like this and then like this, but then they can break and reconnect, and you get N minus K going here and N going here. And then looking at the two cases with the two choices of sign, minus, plus, plus, minus, we get these two dualities. On the left side, we either have O2K plus 1 with an even number of flavors, or O2K with an even number of flavors. And then here we can read off the dual theories. We have N minus K here, so that's O2N minus 2K plus 2N, or O2N minus 2K plus 1 plus 2N, again, for the two choices of sign, whether minus minus or plus plus. Okay, and then we can do, similarly, we can do this with an odd number of flavors. Here we have to have an additional effect. So here, these two 5 branes never touch in the exchange, but we have this extra 5 brane, remember, that we couldn't take outside because it's ending on this 5 brane, right? This lone guy corresponding to the plus 1 in the flavors, and it is linked with the M5 brane. So there will be some non-trivial, maybe non-trivial effect when these two cross, but that's exactly the effect that we derived 5 minutes ago, right? There's this new brane creation effect when the unpaired M5 tailor brane crosses the M5 brane, okay? And there may or may not be creation of a brane depending on the sign, okay? So the number of branes, the number of color M2 branes you end up with is going to be N minus K, and then either plus 0 or plus 1. So the plus minus here is correlated with the upper and lower signs are correlated. So this establishes well, the geometric construction of the duality between the orthogonal theories with an odd number of flavors and the orthogonal theories with an odd number of flavors of the others. And then if you look at the 4 cases that we found geometrically, all 4 of them correspond, can be written more generally as just the original conjecture that Kintaro made, that OK plus N is dual to O N minus K plus 1 plus N. Okay, so for the different cases of N, capital N being even or odd, and capital K being even or odd, you produce the 4 cases, the 2 cases here and the 2 cases on the previous slide. Okay, so I promised to resolve the issue in type 2A, which is sort of really what motivated this work. And so it's informative to understand how the issue of exchanging the NS5 gets resolved from the type 2A point of view. And this is related to the fact that the discrete choice in the extent position of the M5 brane, really the relative position, corresponds to a discrete remnant of a scalar field that lives in the NS5 brane world volume theory. NS5 brane world volume theory is described by 2, 0 tensor multiplet, which has 5 scalar fields. One of the scalar fields is special, it's a compact field. And all those fields will be odd under the orientable projection, but there will be a discrete remnant of the compact scalar, and that discrete remnant will correspond to the discrete choice of whether to put the N5 branes on the same orientable, on the same onto plane, or different ones. Okay, so this is how the argument goes. In flat space, the NS5 brane contains part of its world volume theory, as part of its world volume theory, this Chern-Simons coupling between the rho 1 and 1 5 form and the exterior derivative of that world volume scalar. And this is, for example, what allows us to have bound states of NS5 branes and D4 branes. Okay? So we can sort of turn on n D4 units of 4 brane charge inside the NS5 brane by turning on a flux of this scalar field along the circle, along some circles, and some circle, which is along the NS5 brane. NS5 brane is wrapped on a circle, and we turn on this flux, then we get that many 4 branes. So you can also understand it from the M theory point of view. Basically, you put an M5 brane along X10, you get a D4 brane. If you put it along another direction, you get an NS5 brane. But if you put it diagonally, you get a bound state of NS5 and some number of D4 branes. Now, the orientable projection in type 2A actually projects out this scalar field, actually all the scalar fields of the NS5 brane. It's stuck there, it can't move anymore. But there's a discrete remnant, so it maps phi to minus phi, so the continuous degree of freedom is projected out, but because phi is periodic, there are still two possibilities. It can be 0 or pi, because pi and minus pi are identified. And the case 0 is the trivial case, it's just the NS5 brane. The case pi is something else. It's actually a bound state of the fractional NS5 brane with a fractional D4. Okay, so it's sort of what remains of this integral bound states is a fractional torsion valued bound state, if you like, of an NS5 brane and a D4 brane. And this bound state corresponds to placing the M5 brane on the other OM2 plane. So now you can either have this NS5, so in the type 2A you just have an orientable plane and an NS5 brane stuck on it, but there is a discrete degree of freedom that this NS5 brane carries, okay, corresponding to this discrete remnant of the compact scale of phi, and that lifts the M theory to the discrete choice of putting the M5 brane on the lower OM2 plane or the upper OM2 plane. We can also see this bound state by a deformation, by turning on a twisted mass deformation. Remember, a twisted mass deformation corresponds to taking the D4 brane, putting it on the NS5 prime brane, and then splitting it into two semi-infinite parts. So you have an NS5 brane, then a D4 brane is ending on it, okay, and then the other half of the D4 brane is coming out somewhere else. So in between those 2 points, there's some flux, okay, and that corresponds to, you can think of the D4 brane as coming in, and then it's becoming flux inside the NS5 brane, and it's coming out again. Or you can think of it as an actual D4 brane, a piece of a D4 brane sitting between the two semi-infinite, the points where the semi-infinite D4 brane is connected. And that's what this bound state is. On the other hand, this same kind of deformation viewed from the field theory point of view shifts the discrete data parameter by pi. Taking a single chiral superfield and deforming it by a twisted mass deformation, and then integrating it out, leads to changing the discrete data parameter by pi. So if you do it with an odd number of twisted mass deformations, the net data parameter changes from 0 to pi or pi to 0. And that's consistent with the identification of the discrete data parameter with the discrete relative extent position of the M5 brane. Okay, so it's all the same thing. The discrete data parameter, the discrete relative positions of the M5 branes in the M theory picture, and the discrete bound state of the fractional NS5 brane and the fractional D4 brane. Okay, so this is sort of my last real transparency, and then I'll conclude. Now I can finally revisit the issue of exchange. Okay, so let me consider one example of the theory with the group O2K with an even number of flavors to N. Okay? So this is what the brane configuration looks like in type 2A. String theory, we have an NS5 brane, and then we have not really an NS5 prime brane, but a bound state of an NS5 prime brane on a fractional D4 brane. Okay? So while in the interior we have an O2 minus plane, on the left side it changes in 2 ways, because it goes across both an NS5 brane and a D4 brane. Okay? So this M. Now let's compute the linking number. The NS5 brane has a linking number, which is basically the same formula that we wrote down for in M theory, but now translated to type 2A charges. So it has a contribution counting the difference between the 4 branes on the right and the 4 branes on the left, and a contribution counting the D2 brane charge ending from the left minus the D2 brane charge ending from the right. Okay? Let's exchange the NS and NS. Let's exchange the 2 branes. Okay? So now let's compute the change in the linking number. So the linking number on the left gets a minus 1/4 from here, from the fact that it has a fractional 4 brane on the left, so there's a minus 1/4. And then it gets a contribution of 1A plus 1A by counting the charge difference between the O2 minus and the O2 plus. Right? One is minus 1/8, the other is plus 1/8. And then the linking number on the right-hand side, oh, by the way, you can already see that this is just 0. The linking number on the right-hand side is also 0, because now the 4 brane is on the right side of the NS5 brane, so it contributes a plus 1/4. And now, the orientable planes are different. They're with tildes. Okay, and with the tildes, it's 1/8 minus 3/8. And that's also 0. And so the jump is 0. So there's no change in the linking number. There's no change in the linking number. Then no D2 branes are created. Okay? So before we saw naively that it looked like, to get, if we go from 4 dimensions to 3 dimensions to 2 dimensions, it seemed to require the creation of a single D2 brane. Okay? Now we see that the answer is no, and that was sort of problematic for us. But now we see there's no creation of any D2 brane. There's no change in the linking number.
Don't you have this effect already for all three?
Not as far as I can recall. But that was 10 years ago.
I have to look to work with the board.
I don't remember. I mean, we certainly played this game with those 3 planes 10 years ago. I don't remember, but I could be wrong. But
There is one situation, you have a brane creation, and the other one.
okay.
You just need to figure out which one.
Okay, maybe. And then the dual, you can read off the dual. Well, there's n minus k, the 2 branes in their images, so it's 2n minus 2k, but it's an O2 minus tilde now. See? And so there's a plus 1 here. Okay, I've run over time, so let me conclude now. I'm actually done. So we can derive the orthogonal dualities, and so I haven't shown it. We can also derive the symplectic, the dualities for the symplectic theories as well, using the M-brane configurations. There are new lessons for brane dynamics. The one I showed was sort of extension of the brane creation and S rule in M theory with an OM2 plane background. The results actually extend in a straightforward way to n equals to 4,4 theories. The brane constructions of n equals to 4,4 theories are very similar. Instead of having NS5 and NS5 prime, you just have 2 NS5s which are parallel. Okay? And some of them as well. Most of the results actually extend in a straightforward way for supersymmetries. In particular, it shows that there are 2D theories with 8 supersymmetries where the Coulomb branch is lifted quantum mechanically. And that's kind of unique. We're used to thinking, in 4 dimensions and in 3 dimensions that the Coulomb branch is protected. I mean, the metric on the Coulomb branch is of course corrected quantum mechanically, but it's never completely lifted. Okay? So it turns out in 2 dimensions, with 8 supersymmetries, the Coulomb branch can be completely lifted. In the case of orthogonal and also symplectic gauge theories. In particular cases, with particular matter content. Okay, there are 2 open questions in which we still we're thinking about, but we really don't know, don't have any good direction. And I think it's sort of this is a more general question that is relevant in other dimensions as well. And that is, so I talked about theories with orthogonal gauge groups, but there are actually 3 kinds. So the group, the algebra is the algebra of SOK, but the group can be either O or SO. And actually, there are actually different field theories, and they satisfy slightly different dualities. So in the duality I presented, I was a bit sloppy. Okay? I mean, it is always ON goes to OK with n flavors goes to ON minus K with n flavors and the mesons and the superpotential. But the story gets refined a little bit when you're more careful about whether the group is O or SO. Unfortunately, at least for the type 2A construction, also in the M theory lift, I don't know how to rigorously tell you whether that the construction that we gave is for OK or SOK. And that's not the only 2 possibilities. Within OK, there are also 2 possibilities. So we discussed that there's a discrete degree of freedom, the discrete data parameter. Turns out there's another discrete parameter for OK only, not for SOK. And for lack of a better name, it's called O plus and O minus. It's an additional Z2 degree of freedom, which is related to thinking about the orthogonal theory as an orbifold, as a Z2 orbifold of SO. Okay, so there's an additional Z2, the parity reversing part of OK, which is gauged, and in SO it is not gauged, it's part of the global symmetry of SOK, and if you gauge it, you get OK. So, and thinking of these as, gauging a discrete symmetry in 2D, from the point of view of thinking about this as a string background, requires you to add a twisted sector. And then there's some freedom in how one acts with the projection in the twisted sector, and that freedom is differentiates between these two theories. So again, the dualities, there's a refinement of the dualities and the structure, the counting of the supersymmetric ground states that I presented, that it's actually slightly different for the two theories, actually for the three theories, SO, O plus, and O minus, but I can't rigorously say which of these three theories, sets of theories, we've constructed. Okay? And I'll end here. Thank you and have a great meeting.
Do you have any questions or comments?
So on this last point about whether it's OK or SO, so naively I would have thought the difference is that you'd have something like a monopole type operators and these things would be different. So in 2D though, what is it? You have some operator that on one side it's one thing and on the other side it's another thing, or like in 3D, you have an operator that phase width changes as you go around.
Yes, so
And normally I thought that's the difference in
well, yeah, it's certainly something, associated with the non-perturbative spectrum, like, Ed's old story about type 1 string, Is it SO32, is it O32, is it spin 32 mod Z2? We know, like, for the header, of course it has to be spin 32 mod Z2 because that's what the heterotic dual is. But sort of differentiating between the different groups requires understanding non-perturbative states, monopole operators in 3 dimensions, some instantons, I guess, in 2 dimensions. Yeah, I'm not sure. I mean, I think maybe a simpler place to ask a simpler setting to ask that question, I think, is to look at the 8,8 theories, the maximally supersymmetric theories, by looking at in type 2B at D1 branes on orientifold lines. And there we can, we sort of know, because it's just flat space, we don't cut things off, we just have infinite orientifold lines, and people have computed the full non-perturbative spectrum of D-brane particles in this background, and then, so whether it's O or SO or spin depends on whether you have, for spin you need to ask whether you have particles transforming in the spinor representation, and O versus SO involves some gauge instanton configuration, which is not invariant, has a -1 phase in the path integral under a parity reversing transformation. And so one would have to sort of study the non-perturbative spectrum to see if such a state exists or not. And in this case, it might be more difficult, but maybe a good place to start is with the 8,8 theories that are simply described by infinite D1 branes and orientifold lines. There we know the spectrum of stable, non-UPS, D instantons and D0 branes. And we can analyze it there. Here, I don't have any good ideas so far. I'd love to hear some ideas.
More comments?
Well, I have another question.
Yes.
So about spin K then. So is it possible to have, instead of having chiral multiplets in vector representations, can you do things in spin representations, or is that allowed?
Well, in field theory you can do whatever you want as long as there's no anomalies. But in branes, realizing spinor representations is something that at best you can only do indirectly. So again, unless it's some non-perturbative story like the D particle in type 1 string theory clearly transforms into spinor representation.
Okay, so let's thank the speaker again. we're gonna have a